Hello everybody, it's Andrew Hutchings here, not a licensed physician, just a scientist. And I'm just going to include this from now on in my videos, as I do actually have a degree in it, because YouTube likes to delete videos. But this one should be safe because it's not about coronavirus. Sad that they delete anything about coronavirus that doesn't go along with the popular narrative. But this video is about receptors and how they're not really as simple as you may initially get the impression of. For example, let's say androgen receptors, because it's a fitness channel. Now, I actually don't know about the subtypes of androgen receptors, but if I had to bet, I would bet that in different parts of the body, there are slightly different androgen receptors. And then in certain parts of the body, they may even do different things. Now, a more clear-cut case in point about this are the adrenergic receptors for epinephrine and norepinephrine. So you would think receptors for adrenaline, shouldn't they all do the same thing? Like the adrenergic receptors, they get bound and they do their thing. Isn't that just how it works? And it's actually not. There are different subtypes of receptors, so they're similar but a little bit different, and they can even do almost opposite things. Like the adrenergic ones, if you agonize the alpha ones, it's actually like you're antagonizing the beta ones. It's not exactly the same, but it's like you, on first thought, if you didn't know about all the subtypes and stuff, you would think, oh, let's just get a molecule that mimics adrenaline or norepinephrine. Let's just agonize all the receptors that are for it, and it's gonna do X, Y, or Z. But actually, if it happens to bind to one of them a little bit stronger than the other, you can get very different effects. A good example, since again this is a fitness channel, kind of, I guess it's less of a fitness channel now and more of just a random science and medical and fitness channel. But the estrogen receptors, so people take things like Nolvadex or raloxifene or clomiphene to prevent gynecomastia. And the idea is, in theory, which actually doesn't work out so well in reality, that it is selective for the estrogen receptors that are in breast tissue. Now, perhaps at super low doses that don't actually help anybody in real life, that is the case. But based on all the experimental evidence on humans, and I mentioned it in another video, it was shown that women past menopause, they had deteriorating bones. When given the tamoxifen, their bones got better. You know why? Because it agonized the estrogen receptors in the bones. Even though it's a selective estrogen receptor antagonist for breast tissue. It's not all, right now you're probably going, what? Hold on a second. Tamoxifen, raloxifene, clomiphene, Nolvadex, whatever you want to call them, whatever serum it is, they're supposed to antagonize the estrogen receptors. But it's been shown that they actually agonize them in the bones. Interesting. Now, it was shown that women who were before menopause and had normal estrogen levels had better bones than the woman who had the tamoxifen. But this does also kind of prove that it is a sort of selective receptor antagonist by the fact that, in theory, it should antagonize mammary gland tissue while agonizing other parts of the body's estrogen receptors. The thing is, it's again not always so cut and clear. So while it may agonize the estrogen receptors in the bones, maybe it antagonizes them in the brain. Maybe I don't know about the brain actually for this thing. So yeah, it was a little bit wrong of me to say that it's not really selective. I mean, it's not. As you see, it's complicated. It's bad to just slap labels on things. So yeah, and then another thing is, on top of having subtypes of receptors, I just kind of touched on this with the estrogen, depending on where they are in the body, they can have completely different functions. Like I mentioned it in another video, NMDA receptors, they're mostly thought of as inhibitory receptors for analgesia, to block nerve transmission, to conduct anesthesia. Sadly, we don't use them enough in medicine for people who have bad pain. But if you were to ask 100 doctors, is there any stimulatory, how would I phrase it quite right? Now, if you said, is there any stimulatory effects of something like ketamine or phencyclidine, which is PCP? Of course, if they actually know about these things, they would say yes, because it has dopamine and norepinephrine agonizing and other modulating properties. But in fact, the NMDA receptor properties of the molecule itself have stimulatory and suppressing properties. There are different NMDA receptors in different parts of your brain. When you hit them with an antagonist, like ketamine, it doesn't always do the same thing. We just don't, to my knowledge, have molecules that can selectively target specific NMDA receptors. I think that once we can have those, that there are some, I believe, that will allow people to learn languages a lot faster. There's probably going to be a lot of other uses as well, but they do actually enhance brain function when blocked in certain parts of the brain and certain subtypes of the receptors probably. Whereas for the most part, it's like you're wasted on alcohol. But no one would suspect that they actually do stimulate parts of the brain. So yes, bottom line is receptors are complicated. There are subtypes. They are different in different parts of the body. They do different things. Just because something agonizes one doesn't mean it agonizes the other. Just because it agonizes it doesn't mean it doesn't actually also antagonize it a little bit. And just because it agonizes it doesn't mean it agonizes it the same way as the natural thing that binds to it. Oh, and then you probably heard a lot about, if you're into fitness and maybe you watch other channels, like androgen receptor upregulation or downregulation, or what is that exactly? Long story short, that is when your genome decides to shut down your body's ability to read it and print out more receptors. Receptors are just proteins. So the DNA goes to RNA. I mean, a lot of stuff has to happen, but long story short, DNA goes to RNA. RNA prints out one amino acid at a time until they go and they crumble together based on their electric properties, like where the electron density is, and they fold in a certain way, and they form a protein. That protein is a receptor. Well, it can be a receptor, it can be an enzyme, but they're all just proteins. So yeah, when you hear of upregulation, it just means that now you got more molecules going maybe on the DNA side, or maybe probably more likely, I mean, it's really hard to say because it could be on the DNA side, could be on the RNA side, but somewhere along the line you got other molecules that are influencing how open the DNA is to being read, or how long the ribosome is clamped down on the RNA that reads it out one amino acid at a time, or it just changes how fast or how many are made. And downregulation is, first of all, it can be, I think I made a video just yesterday about this, how receptors can be like endocytosed, they can be tagged for destruction, and they can also have the genome like close up, or the RNA things change, and then it doesn't print out more of them as much, so you end up with less. And my mom is calling, so you can hire me on my website, andrewhutchins.org, for consultations. Please like and comment.